Welcome everybody. We're going to be talking about the mean value theorem in this lesson. And you may have noticed that I don't have the mean value theorem listed. I have the intermediate value theorem, which is something we've learned already. I don't want to confuse the two theorems with each other. They both get used a lot. In fact, there's a third theorem called the extreme value theorem. We're going to touch on all three of them today, but really the mean value theorem is the star of the show. So first of all, the intermediate value theorem, as you may remember, was a theorem that simply said, hey, if you start, I believe my example was, if you start in Seattle and you end up the next morning in Edmonton, Alberta, Canada, that means that somewhere you must have crossed the border. It had to happen at least once, I should say, maybe 3 times, certainly an odd number of times, but you had to cross at least once. And furthermore, if Seattle is at 48 degrees north latitude and Edmonton is at 54, which they are, I looked it up on the internet, and the international border is at 49, not only did you cross 49 north, but you crossed every latitude between 48 and 54 at least once. That's what the intermediate value says. This line is y equals k, and you had to cross it at least once, somewhere between Seattle and Edmonton. Okay, so that's old news. We know that already, and we're going to go ahead and move ahead to the mean value theorem, which is today's lesson. Okay, the mean value theorem, or MVT, involves the derivative. It says that the derivative at C is equal to f of b minus f of a over b minus a. Now, the devil is in the details here. You have to say that the function's continuous between a and b, including the endpoints, notice the hard brackets, and that the function is differentiable or has a derivative in between a and b. If you get through those first two hurdles, then somewhere between a and b, in a place called x equals c, there's a number that satisfies this theorem. Okay, why is this important? Well, we're going to see a few examples coming up later on in the lesson that will make that crystal clear. This also is absolutely guaranteed to be on the AP exam. Usually as a free response question, a lot of times they'll work it into multiple choice as well. So basically, if you have a function, we'll call it f of x, looks like that. And let's say you start at x equals a, and over here we'll end at x equals b. What you do is you take the overall slope between a and b. In other words, good old middle school slope here, rise over run. So if you're starting here and you end up here, your slope's probably 1/5, 1/6. It's not very steep. It is positive. What the mean value theorem says is that the derivative, f prime of c, which we know is the slope of the tangent line, it has to match at least once. And you can see that there are 3 places where the green is parallel, same slope, to the blue. And those places, if you take it down to the x-axis, are called c. Lowercase c is the variable that's always used in the mean value theorem. It's just the variable of choice. If I was to walk into a random AP calculus class and I didn't hear anything until I walked in and I saw C's on the board, I'd figure they're probably doing the MVT. All right. If you have a slope of 0, it's a special case called Rolle's theorem. And all Rolle's theorem is that it's MVT except the slope is flat or horizontal. So let's say the function f of x goes through the point 1, 3 and does its thing and ends at 10, 3, or goes through 10, 3. And the overall slope between 1, 3 and 10, 3 would be 0, of course. They're at the same height. Well, Rolle's theorem, which is really just MVT, says that if the overall slope is 0, that the tangent line has to have a slope of 0 at least once. And sure enough, you can actually see 4 different times where that happens. And again, those places, those x locations, are called C. And the mean value theorem guarantees that there has to be at least one of them in between A and B. When I say in between, the endpoints are not allowed. Let me go back to the fine print here. You can see that the mean value theorem specifically says there exists a number C in A comma B, but the interval is a open interval. If you get A or B as an answer, you have to throw it out. You have to discard it. And I will try to trick you to see if you're going to fall for that. College Board will oftentimes try the same thing. Okay, let's do a practical example of MVT. We're going to take a road trip from Cleveland to Chicago. Why not? All right, Chicago is 330 miles away. I know because I've made the drive many times. So let's say we start right downtown in Cleveland at Public Square. We have the time axis, which is typically the x-axis in science class. We'll call it t. And distance, we'll call that d for distance. That's the y-axis. And so what we have here is two vehicles. First off, we have me. I'm driving my car, and I'm very careful. I'm going to go a constant speed. So I take off from Cleveland. I've got snacks in the car. I've hit the restroom. I don't have to stop. I'm going to plow straight through to Chicago and just hit cruise control, stay in the right lane on the turnpike. So if it's 330 miles away and I arrive in Chicago 6 hours later, I know because it's the point 6 comma 330, you can find my average velocity or average speed. 330 divided by 6 is 55, so I'm on cruise control at 55 miles per hour. I'm the driver nobody likes on the turnpike because the speed limit's 70. I better be in the right lane. All right, you guys take off in a rented limo, a party van, if you will, and you're taking turns driving it, which is probably a nightmare legally. But anyway, you do that, and you start out same time, same place as me, but you take off faster than 55 on the turnpike. Get about 150 miles out, and people are like, hey, we need a restroom break, we need to stop, we're hungry. And so you pull off, and obviously your velocity is 0 for a while as you're at Bruegger's or Starbucks or one of the toll plaza places. And as you're there, you look out and you see me driving by. That would happen right there. And you're like, yeah, there goes Luz. And so you probably think, hey, let's go catch him. Okay, so you jump back in the car or party van, and you're going faster than me, steeper slope. So eventually you're going to pass me on the turnpike right here. Of course, I won't look over at you. I'm like just driving straight. And then this happens once more. We get closer to Chicago, maybe Valparaiso or Gary, Indiana, somewhere. And again, you pull off and I pass you on the road. But then you catch me right as we cross the border into Chicago from Indiana on the Skyway toll bridge. And we get there at the same time. Okay, good story, but let's relate it to the mean value theorem. My average speed was 55 miles per hour the entire trip. That's middle school slope. That's rise over run. You went 330 minus this 0 down here in Cleveland over 6 minus this 0. You probably didn't even think about the zeros, but you did middle school slope. That's equal to the derivative. That means that at least once during the trip, probably during the on and off ramps of service plazas, your digital readout also had to say 55. You had to be going 55 miles per hour at least once along this trip. Because if you weren't, if you never reached 55, you're going too slow, you wouldn't have reached Chicago. You never would have caught me. If you were going faster than 55 the whole way, I wouldn't have caught you. You would have blown me away and never looked back. Plus, you would have jumped into a moving vehicle going at a high rate of speed, which probably isn't wise. But since you had to hit 55 at least once, and here are the places that it happened, the mean value theorem holds. And again, the prerequisites for this are that both of the trips in our cars had to be continuous. You didn't suddenly leave the road, nor did I. And we actually arrived in Chicago when we left from Cleveland. We didn't go missing, which obviously was the case. So there's a good example of where the mean value theorem is true in real life. All right, math example number 1. Given the 3 functions below, Determine whether or not we're able to use the mean value theorem. Are the conditions of the MVT met? If they are, if so, locate the value of C by just drawing the parallel tangent secant lines. Here we're going to have to estimate or guesstimate C. Later on, we'll actually calculate it perfectly. Okay, so first things first, part A, I'm going to draw a secant line where secant touches the curve twice. Okay, between 3 and 7. And then I have to find what looks to be a parallel tan line. So I'll go ahead and try that out. And I think I can see where one is if I kind of grab this and do this. Those are parallel. And it looks like right about here is where it hits the curve. If I take that down, I'm going to laugh at how I can't draw straight lines, but that looks like C is about 5.5. And again, you can be close. You can say 5.4, 5.3, 5.6. Again, we're just estimating it. Okay, part B. Again, I connect the two dots, making a secant line. It crosses the curve more than once. And then I come up with some parallel lines as well. And those parallel lines can serve, since they have the same slope, as the tangent slopes. See, there's going to be one right about here. And another one right about, let's say, here. And if we take that down, the values of C, there are going to be 2 of them this time. Again, there's no way in this problem to tell exactly what they are, so I'm just going to make a guesstimate. C looks to be about 2.2 or so-ish. And again, there's a second value right around, say, 5.7, I'll call it 5.8. All right. Last but not least on this part, example C. I connect these. That slope, if I wanted to get accurate, let's see, that's up 2 and over 1, 2, 3, 4. That slope is 1/2. The mean value theorem says the slope should be 1/2, somewhere between 1 and 5. But you know what? It's not. This is too steep, and this is negative. Right here, there's a cusp. There's no slope at all. So this is supposed to be a theorem, mean value theorem. How come it doesn't work? Theorems are supposed to be true all the time. And the reason why it doesn't work is the conditions were not met. Ouch. Because there was a cusp in between 1 and 5, there was a cusp at 4, that means that the function was not differentiable the whole way on the open interval 1 to 5. Therefore, the mean value theorem doesn't apply. It's not that it doesn't work. It works. It works all the time. It's a theorem. It just simply can't be used here. The prerequisite conditions were not met. Notice in A and B, they were. You had functions that were smooth, they were continuous the whole way, and they had derivatives, they were differentiable. All right, finishing up on number 1, we have parts D and E. This time, instead of graphs, we have equations, and we have the intervals. So first off, part D, we're going from 0 to 1. We have a square root, and if I plug the 0 in, I do get the square root of 1, which is 1. If I plug the 1 in, I get the square root of 0, which is, of course, 0. So it is continuous. If you plug in numbers between 0 and 1, you won't have imaginaries. You're safe. So it's continuous the whole way. If I were to graph it, it would look like this. It would actually be a quarter circle in quadrant 1 is what it would be. And so mean value theorem does apply because it is, as I mentioned, continuous and differentiable between 0 and 1. And so there must be a place where the slopes match. Now the middle school slope, if you will, or rise over run, would just be -1. That's the slope of the secant line. So therefore, the slope of the tan line must also be -1 somewhere. Let's do a nice little parallel segment here. Let's say that's going to be right about there. Again, this is just a complete estimate. If I drop it down, right about there. Okay, again, in future examples, we'll give the exact answer. For now, we're just kind of drawing and looking. Part E. Oh boy, absolute value. I gotta remember how to graph that. It's gonna be a V shape, but it's opening upside down. Man, All right. I could start to graph until I realize, wait a second, I'm not doing this problem. The mean value theorem doesn't apply because there is going to be a corner at x equals 3. In fact, actually, if I did graph it, the vertex here would be at 3, 3. It'd be right here. And the graph would open downward. But since there's no derivative here, since it's not differentiable, and you have a corner, and that's smack dab in the middle of the interval, the mean value theorem simply does not apply. All right, so that's example number 1. All right, number 2, instead of estimating the values of C, we're actually going to find the exact values of C that satisfy the mean value theorem. All right, so first of all, does the mean value theorem apply? Well, this function f of x is continuous between -4 and 5. If you put the -4 in, you get the square root of 9, which is 3. In fact, that's useful. Let me write that down. If you plug the 5 in, you get the square root of 0, which is, of course, 0. And all values in between -4 and 5 would keep that real. You know, you would not have an imaginary number. If you put a 0 in, let's say, or a 1, it would still be positive radicand. So the mean value theorem is in play. All right, the mean value theorem, in fact, let me go back to the definition. I don't know if you realize this or not. The mean value theorem is simply slope equals slope. This is high school slope, known as the derivative. It's the slope of the tan line. And then over here, this is just the slope from middle school. It's y2 minus y1 over x2 minus x1, disguised as a's and b's. Really, the mean value theorem simply says slope equals slope. So if you have trouble memorizing it, now it's easy. All right, back to problem 2. So let's find the aforementioned middle school slope. We'll go y2 minus y1. I'll say 0 minus 3. I'll start here, which means I have to start with the 5 minus -4. That's going to be -3/9, which is -1/3. All right, halfway home. Now we'll get what I call high school slope, the slope of the tangent line. That's going to be the derivative. Before I take the derivative, let me rewrite this. F of x is going to be 5 minus x to the 1/2 power. I just make it easier. And so the derivative, 1/2 in front using the power rule. 5 minus x goes down by a power, so that's to the -1/2, times a chain rule of -1, which I'll throw in front. All right, so that's the other portion of this. And we simply need to set these two items equal to each other. And I'm going to make myself some more room to do just that. There we go, plenty of space now. Since both sides are negative, I'm going to go ahead and multiply by -1. That'll knock the negatives out. And I'm going to go ahead and rewrite this as 1/2. And then the 5 minus x will be down here as a square root. So it's square root of 5 minus x in the denominator. That takes care of the -1/2 power. 1/3 come on down. When we cross multiply, you can see that we just get 2 square root of 5x. It's going to be equal to 3. 3 times 1. You've got some algebra options here. I think I'll go ahead and divide both sides by 2 first. You could also square both sides first. I'm going to do that step next. The order doesn't really matter there. So I divided both sides by 2, and now I'm going to square both sides. You have to be careful when you square both sides in Algebra 2. It's a legal move, but sometimes you get extraneous answers that have to be thrown out. So just be aware. 3/2 times 3/2 will be 9/4. I'll continue on with my algebra. I will subtract 5 from both sides. Let's see, 5 would be 20/4. Write it like that. So we have -x equals -11/4, which means x is going to be 11/4. Or 2 3/4 if you prefer. 2.75 is fine. Notice I changed the x to a c for absolutely no mathematical reason. C is our variable of choice when we're doing mean value theorem. And I do have to make sure that 2 3/4 is in the proper interval. It should be, because mean value theorem guarantees at least one answer. And yeah, 2 3/4, 2.75 is safely in between A and B, between -4 and 5. So that's a good answer. 2.75, we'll go with that. That's it for number 2. Okay, moving on to number 3, we have a cubic, and we're going from -2 to 3. I know that the cubic function's going to behave just fine, so it will be continuous and differentiable both, so no worries there. Let's go ahead and plug the points in. -2 cubed, that's going to be -8 plus 8 plus 4. That'll be 4, that's easy. If I plug the 3 in, 3 cubed, that's 27 minus 4 times 3, 12, plus 4. Let's see, 15 plus 4, that's 19, so 319. Okay, so the slope of the secant, or the middle school slope, will be 19 minus 4 over 3 minus -2. We're looking at 15/5, and of course 15/5, better known as 3. So that's the first part of our deal. The second part is to do the high school slope, also known as the derivative. So that's going to end up being 3x squared minus 4. And we'll set those two boxed up things equal to each other right now. So we have 3x squared minus 4. Notice I'm remembering to change the x to a c. Usually I'm doing that on the last step right by the answer, but I remembered early this time. Add 4 to both sides. Now it's just algebra 1 at this point. So we have 3c squared equals 7. That means that c squared will be 7/3. Square root both sides. Since I'm putting the square root on, I need a plus minus on the right. And c will be plus or minus 7/3. Square root of 7/3, I should say. And both of those answers, I believe, are good. I'm going to double check. I believe that they are both in between -2 and +3. The positive answer is good for sure. Negative square root of 7/3. Yeah, they're both good. 1.5 and -1.5 are both going to be keepers. So we actually have 2 answers here instead of just 1. All right, that's number 3. Moving on. All right, here in number 4, I think I'll use red this time. If we take a -3 and plug it in. Oh boy, here, let me do the +3 as well. Maybe I'll do the +3 first. That'll be a little easier. Maybe I'll do neither of them. I don't have to do this question. You know why? We've got some serious discontinuity in the form of a vertical asymptote. At x equals -2, and -2 is on the interval. We don't have differentiability the whole way, so thank goodness I actually didn't plug the 3's in. Maybe you did. I've always learned that I check first before I go crazy. The mean value theorem simply does not apply here. And you want to write a quick explanation, which sure beats doing the problem. You want to say the mean value theorem doesn't apply, but you also want to say why. College Board's going to expect that. I will expect it as well. You want to say it's not differentiable if x equals -2. You can mention the vertical asymptote, but the key is to say it doesn't have a derivative. It's not differentiable. All right, those are the kind of homework problems you root for. Less work. Why do we learn this? This is probably the most famous application of the mean value theorem. I know out on the East Coast, my friends from New Jersey said that they used to do this on the turnpike. I don't know if it's still a thing or not. But you can actually catch somebody speeding without even witnessing the speeding, which is terrifying for me personally. Let's say that you have this dump truck. I found it on the internet. I thought it was kind of cool, so I used it. And the dump truck is going along this road, speed limit 55. It passes the first police officer at 55 miles per hour. I was like, whew, okay, good. Saw him in time. And then 5 minutes later, 6 miles down the interstate, the truck passes a second cop car. Same speed limit, but now the truck's only going 50 miles per hour because for some reason people have to go way below the speed limit when they see a police cruiser sitting there. So nobody has witnessed this person speeding, yet the MVT guarantees it. This truck can be pulled over later and given a ticket or mailed a ticket, and the ticket would hold up in court. They would have some sort of expert like myself come testify. I'd throw the mean value theorem at the judge, and the ticket would be issued. How can we prove that this dump truck is speeding when nobody witnessed it? And here's the answer. You can find the average speed, which is sort of like the middle school slope, if you will. And that would be, well, let's see, 6 miles apart, so that's 6 miles. 6 minus 0 if you want, because this would be like 0 miles, and this would be 6 miles. And then 5 minutes have gone by. That's 5 minutes minus no minutes. So basically, this truck has gone 6 miles in 5 minutes. And from here, it's just good old dimensional analysis from your science class. You have to figure out what's that in miles per hour. So we want to get rid of the minutes. So we'll put minutes up top. That way they cancel. We'll put hours on the bottom. That way our answer is in miles per hour. Let's see, 1 hour, 60 minutes. That looks good. We can do some light canceling with the 60 and the 5, divide them by 5. And 6 times 12 is going to be 72 miles per hour. So this dump truck right here was averaging 72 miles per hour in between the cops. Sure, the police didn't see the person speeding, but the mean value theorem says if the average speed was 72 between the two cars, that the truck actually had to go 72 at least once. To be honest, if the cops saw the dump truck going 55 and 50, then we know that the truck actually went faster than 72 to make up for it. So a ticket could be issued and it would stand up. So that's one interesting use of the mean value theorem. What's really terrifying is any turnpike, when you think about it, you get on and you get a ticket or you have iPass or whatever, and they know what time it was and they know where you are. And when you get off, it's almost like you're tattling on yourself. So my advice would be if you ever travel on the turnpike or a toll road and you want to speed, maybe you shouldn't speed, but if you happen to speed, stop at a rest stop or something at least once, and then no one will know. All right. Okay, we'll wrap up this first day of mean value theorem with just a few things to keep in mind. They're hiding behind here. The first one is this. The function must be, and I hope you know what I'm going to say, continuous on the closed interval AB, and, yeah, you know it, differentiable between A and B on the open interval. If it's not, stop. You can't do anything. Don't waste your time doing any computations. The mean value theorem doesn't apply. The second of three things. Your answers must be on the interval. Okay, let's say the interval was 1 to 5 and you get an answer of 6. You have to throw that out. Now, there has to be at least one answer in there. But if you have a second, third, fourth answer, you've got to check those. And finally, last but not least, what if you have an answer that is right at A and right at B? Well, those are border points, and the border points are not allowed to be answers. They're not eligible. If you have a border point, you have to pitch it. And the reason why is because the mean value theorem states there exists at least one value C between A and B, and they curl the A and the B. The endpoints are not eligible. So that's it for day one, mean value theorem. Take care. We'll see you for the next part. Bye-bye.